Thank you. Thank you for having me. It's lovely to be back here. Okay, so I'm going to tell you about some recent work with Amir Yehudayev about the gap Hamming problem in communication complexity and its connection to anti-concentration bounds. So let me just start by stating what the gap Hamming problem is. So the setup is like this. You have two parties, Alice and Bob, and each of them has a string from the cube. Okay, so Alice has X and Bob has Y. And they're promised that the inner product of X and Y, these are plus minus 1 vectors, the inner product has magnitude that's at least squared n. It's not close to 0. Okay, so the goal is for them to determine whether or not the inner product is positive. So does the inner product have magnitude bigger than squared n or less than minus? Is it bigger than squared n or is it less than minus squared n? So that's a communication problem. And the question that we're interested in communication complexity is how long does their conversation need to be to answer this question? How many bits do they need to communicate to answer this question? Now, let me make a few comments about the way I've set up this problem. So the first is that the title says gap Hamming, but this is about inner products. The normal way in which this problem is usually set up is that the promise is that the Hamming distance between X and Y is either bigger than n over 2 plus squared n or less than n over 2 minus squared n. And you want to know which of those two cases you're in the communication problem. But for the math to work out later, it's much more convenient to think of everything as inner products. And the inner product here is the same. Computing the inner product is the same as the Hamming distance. So I've moved to inner products. It'll make the notation much nicer. And the second comment that maybe it might seem strange if you haven't seen this before is y square root n here in the promise. And that's because that's the most interesting setting of parameters. When the promise is stronger, that it's much bigger than squared n, then actually there are sort of easy protocols that you can run. You can randomly sample some coordinates and estimate this thing. And eventually what we're going to show is that at squared n is when the problem becomes really hard for the players. They really need to communicate a lot of bits.
So this is all randomized?
Yeah, this question, I'm not, at this point I haven't committed to it, but eventually we're going to prove that even randomized protocols will require large.
This talks about randomized communication complexity.
Yes. Sorry, you cut out a little bit, but you can think of it as randomized communication complexity if it helps. Okay, so I'm going to be more concrete soon when I start stating theorems. So for now, I just want to give you a high-level picture of what the problem is. Now, another version of this problem, which is even easier for the parties, is the exact gap Hamming problem. Here, it's exactly the same setup, except the promise is now much stronger. The parties are told that actually the inner product has magnitude exactly squared n. So the inner product is either plus squared n or minus squared n. These are the only two options. And then again, the question is how much do they need to communicate to determine which case they're in. So those are two communication problems. And I want to tell you a little bit about how Amir and I got interested in this question. Recently, we published a textbook on communication complexity. And this is the cover of our textbook. And the reason Amir and I were drawn to writing this textbook and to working in this area is because communication complexity has two very nice features that are also shared by the gap Hamming problem. So I feel like the gap Hamming problem is a prototypical communication problem. So what are those two features? The first feature is that the model of communication complexity is extremely mathematically clean and nice. And that means that a lot of old, deep, and beautiful ideas from mathematics, these ideas here, can be used to reason about the same thing, communication complexity, on the one hand. And on the other hand, the model is extremely natural. It's hard, maybe impossible, to imagine any model of computation that does not involve communicating components. Okay, and and sure enough, results in communication complexity have been used to reason about a huge, diverse collection of computational settings that seem like they require completely different mathematics when you first look at them. Okay, so so this is sort of the picture that motivated Amir and I to work in this area and also write this book. Communication complexity sort of forms a conduit between really beautiful ideas in math to many practically motivated questions. And if you work in communication complexity, the real reason we're interested in this, you get to play with all kinds of math. Okay, this is what you end up doing, is doing all kinds of learning all kinds of nice math. And one of the main reasons I like this work is that in understanding this question, we discovered a new way to apply another really well understood and old idea in math, Fourier analysis, in a new way. We applied it to communication complexity and used it to prove lower bounds. So that's what I'm going to show you today. Okay. So independent of this problem, I find it interesting because it's a connection between how to use Fourier analysis to reason about communication complexity. The gap Hamming problem itself, I said it's a prototypical example of a communication problem because it's, again, a very simple problem, but a wide variety of mathematical ideas have been used to reason about it. It's the kind of problem that I like. It was first posed by Indick and Woodruff, who were working in streaming algorithms on the application side. And they observed that that what they were really trying to understand was this communication problem in understanding their streaming problems. And they asked, what is the communication of this problem? And that remained open for almost 10 years before Chakrabarty and Regev proved that linear communication is required. Alice and Bob must send n bits over in order to compute the answer here. And Chakrabarty and Regev's proof involved this analogy between the cube and Gaussians. So I'm not going to get into details at all, but I'll just say what they managed to do is they took this question, which is about points in the cube, and they translated somehow to questions about samples coming from Gaussian space. Then they reasoned about that space and then managed to translate the result back to the cube. So it's quite a complicated paper, I would say, but really beautiful. And then a couple of years after that, Shurstov came up with quite a different proof. His proof uses matrix analysis, the singular value decomposition, and an inequality of Talleyrand about projecting points in the cube to subspaces. And then maybe around the same time, Vidic came up with another simplification of more along the lines of Chakrabarty and Regev to prove all these are proving the same result. And when Amir and I first encountered this problem, we never really thought about it, but then we wanted to write this result in the book because it's such a fundamental problem. And so we had to try and understand which proof to write in the book and how to try and simplify it. So we worked on it quite a bit. Eventually we wrote Shurstov's proof after we simplified it a little bit. So that's what's in the book. That's what's in the book. And sure enough, about 2 months after we turned in the final draft of the book, we came up with a fourth proof, which is the proof I'm going to show you now. So this proof is not in the book, but it's in some sense, I think the nicest one. It gives exactly the right constants and the right bounds. So there are lots of proofs about this problem. I'm going to show you the ideas for one of them. Okay, so that's a little bit about the history. That's about the gap Hamming problem. Now, the the exact gap Hamming problem was actually posed when Chakrabarty and Regev came up with their proof. They suggested it as an open question. And they also observed that in some settings, the exact gap Hamming problem is much easier than the gap Hamming problem. For example, one simple observation is that actually with just 2 bits of communication, in fact, if Alice and Bob just compute the product of all of their coordinates, then this actually determines the inner product modulo 4. Okay, so that's the claim, and here's one way to see why it's true. It's not a full proof, but if you think about it, if you flip one of the coordinates here, flip one of the coordinates from 1 to -1 or -1 to 1, then it changes the sign of this term. And it changes this inner product exactly by 2 modulo 4. Either it increases it by +2 or decreases it by -2. Either way, it's changing it by 2 modulo 4. Okay, so that's some intuition for why this actually determines this inner product modulo 4. And that means that if, for example, squared n and minus squared n are not equal modulo 4, which can happen for some values of n, then this 2-bit protocol actually, where Alice sends the product of her inputs, Bob responds to the product of his inputs, that protocol will compute, will solve this exact gap Hamming problem with just 2 bits of communication. But it's not at all clear what happens in general for general values of n.
Excuse me?
Yeah.
Can you maybe specify what do you mean by communication required, the amount of communication required? How do you quantify?
So I will say a little bit about the model of communication complexity, but actually I mostly want to spend my time talking about something a little more technical. So if it's maybe I'll say a little bit. So a valid protocol here actually is, the protocol here would be that Alice sends the product of the bits x, and Bob sends a response with the product of the bits y. That's 2 bits that they're exchanging, and this determines the value of the function. More generally, a protocol is where Alice sends a message that's determined by her input. Bob looks at the message he received, and then responds with a message that is determined by his input and the previous messages, and they continue to communicate in this way. So protocol is given by a sequence of functions that say how each player will compute the next message based on previous messages and their input. And the communication complexity is the total number of bits that they can communicate in any execution of the protocol. So that's the definition. You won't need to
functions.
Say again?
That's the number of functions or the number of steps in the protocol?
The number of bits communicated is the thing we're trying to optimize. The total number of bits communicated. So imagine that every function can send multiple bits. It's the total number of bits. Okay, so this thing implies the existence of a very short protocol for some values of n for this problem. Any other questions? Before I start proving things, I will state the things, the setup very precisely. So
there's something where you can say like this parity is the only case. Like if you can't have this parity, it's not any, if it's root n to root n plus 100 or something, it's like in that range, then you can't say anything because you can't do this parity argument. Or like you have some result that says if you weaken this exact problem a bit, it's just as hard as.
We will probably see it, Ryan. We will probably see exactly what they can prove and what to be fair for me. So.
Okay. So this was the state before before our proof, and we actually proved that, in fact, that counterexample is a pathological case. In general, there are infinitely many values of n where really omega n communication is required. So that's something that our proof can do that the other proofs we'll see why what's different in a second. Okay, so as I said, I'm not going to I don't want to be very precise about communication complexity because we don't really need the model. We just need one consequence of the model or one feature of the model, and that's what I'll explain now. Which is that small communication protocols, cheap communication protocols correspond to partitioning the space of inputs into a small number of combinatorial rectangles. Okay, so in this picture, imagine that Alice's input corresponds to every row of this matrix, and Bob's input corresponds to every column of this matrix. Every input of Bob corresponds to a column of the matrix.
Do you need to flip the slide? We don't see
Oh,
a matrix here.
It stopped updating. Okay, it should be back. Oh, no. Now it should be back. Is it good?
Yes.
Okay, yeah. So think of all the inputs of Alice and Bob as corresponding to rows and columns of say this matrix. And what they're trying to compute is an entry of the matrix. Okay. Alice knows the row, Bob knows the column. They want to know what is the value of the entry. And then if you take any communication protocol, it turns out it corresponds to a partition of the matrix into rectangles. Because let's say, Bob speaks first and Bob sends some bit that depends on the column that Bob knows about. Then this means that some set of columns will lead to the transmission of that bit. So it restricts the space of inputs that the players are working with to this submatrix. The submatrix that corresponds to the columns that would lead to the bit transmitted by Bob. And now if Alice responds with another message, that restricts the set of rows to a smaller set of rows. And in this way, as the parties communicate, they're moving to a smaller and smaller submatrix until eventually they stop communicating, at which point they've isolated the submatrix where they presumably know the answer to the question they were trying to answer. So the upshot is a protocol with small amount of communication corresponds to a partition of the space into few rectangles.
And each one has constant value.
And each one, the value, it may not be, for example, in our setting where they're trying to compute the gap Hamming problem, it means that you would hope that in each one, whether the inner product is positive or negative is determined. Okay, so, and this picture works, even if you're thinking about randomized protocols, this picture makes sense. Then you will have that in each one, the value of the output is mostly determined. It's mostly. Okay, so the upshot of this picture is, and now I'm going to get more formal and more rigorous, is that it turns out that understanding this question, this gap Hamming question, to understand it, what you really want to understand is the following type of question. You want to understand how the inner product behaves in large rectangles. Okay, so let's say that you have a set A that's a subset of the cube, and a set B that's also a subset of the cube. And X is uniformly random in A, Y is uniformly random in B. And just very broadly, what we want to understand is what can you say about the distribution of the inner products X and Y if all you know is that the rectangle is large? This is the total number of entries in the rectangle. So if I know that that quantity is large, what does it say about the distribution of the inner product? That's
large is still exponentially small in n. But
yeah. I'm gonna tell you exactly what large means in a second. Yeah. So, but at a very high level, this is what we want to understand. And now I'll show you exactly concretely what did all past work prove. Proved a result that's exactly of this type. They showed that if the rectangle has size bigger than 2 to the 1.99 n, so just to remind you, so here we're working with n-bit strings. So 2 to the 2n is the size of the entire space. Okay. So what they show is that as long as the rectangle has size 2 to the some number slightly smaller than 2 times n, then the probability that the inner product, the magnitude of the inner product lies near 0 within a squared n over 100 of 0 is bounded away from 1. It cannot be that you can find such a large rectangle where all the inner products, the probability of being in this small window around 0 is very, very close to 1. That's what they show. Okay, so now I hope that the statement, this statement is really, it's clear what the definitions are and what we're talking about. If it's not, please ask me a question.
Anup, why is this relevant to the actual problem? It's why this statement is relevant to the actual problem. These are the inputs we don't care about. We are promised we don't. The inner product is not close to 0.
Yeah, that's right. Getting from the actual problem to this requires some non-trivial steps. So what they actually do is they start with the gap Hamming problem, and then as Shersov presents it, I think that's the cleanest way. He switches to a different problem where they're promised that the inner product is either very close to 0 or very far from 0 first. This is the first switch he makes. He shows that understanding that is good enough to understand the gap Hamming problem. And then you're in this setting where these rectangles matter. And the other papers also do the same thing, actually. Eventually, they boil it down to this, the question about this kind of question about rectangles. Okay. Okay, any other questions? So this question is going to be the focus, or this kind of question is going to be the focus of my talk from now on. And what we do in our work is actually just give all the right constants and the right values for this question. And in fact, we prove even stronger results, as I'll show you in a second, about the inner product in such rectangles. So before I tell you what we prove, let me show you a couple of examples that should guide what the correct answer should be. Okay. So the first example, the first observation is that even if you take A and B to be the entire cube, okay, then near the middle, the probability of seeing, the inner product of 0 is this is just a binomial distribution. So the probability of seeing the middle value is 1 over squared n. Okay, and in fact, so squared n is sort of the right, in a squared n size window, you will see most of the probability mass, and even this rectangle. So squared n is sort of the right kind of quantity to be thinking about here. The second example is that as soon as the rectangle is of size about 2 to the n, then there are examples where the inner product is just a constant. Okay. For example, if you take A to be the set of inputs where, say, the first half is fixed to 1 and the remaining coordinates sum to 0, and B to be the set where the first half sums to 0 and the second half is fixed to 1, then the inner product of any vectors x and y from A, B will be 0, but the size of this rectangle is very close to 2 to the n. Okay. So I cannot hope to prove many interesting results for rectangles that are of this size. Now let me show you what we prove. Our result will really navigate these two extreme points. So what we show is that if as soon as the size of the rectangle exceeds 2 to the n in the exponent, meaning it's 2 to the 1.01 n, then you really get a pointwise anti-concentration. The probability that the inner product will be any fixed integer is bounded by 1 over squared n. Okay. And this implies the previous kinds of results I showed you, because if, for every integer, the chance of being there is 1 over squared n, then if you take an interval of width squared n, squared n over 100, then the chance of being there will be bounded away from 1, just by the union bound. So that's one result that we prove. A second, and in fact, we prove stronger statements. The second one, this one, for those of you who know extractors, it's like a strong extractor version, which is that under the same setup, if you have a large rectangle, then we show that actually with high probability over the choice of x, even after you fix x, the probability that the inner product is equal to any fixed integer is at most 1 over squared n. So this is an even stronger statement. And the strongest statement we prove is, again, under the same setup. So if you have a rectangle of this size, then with high probability over the choice of x, in fact, it's true that the probability that you see k minus the probability you see k plus 4 for any integer k, this is bounded by 1 over n. These two probabilities will be very close together. So this is the strongest statement we prove. Now, maybe it's not, I wonder if, I wonder if someone can see why, maybe it's not immediately obvious why theorem 3 implies theorem 1. I wonder if someone can see. So theorem 3 actually is stronger than theorem 1. It implies it. I wonder if someone can see why that's true.
You can add up over the values, +4 +8.
Yeah, exactly. Yeah. Yes. Hi, Mark. Didn't see that. Yeah. So if you have a single point which has probability, 100 over squared n, then that point +4 will also have probability very close to 100 over squared n. And if you take squared n steps like this, this error is small enough that even after squared n steps, all the probabilities will be large, and this will give you a contradiction. You cannot have a single point that violates theorem 1, a probability bigger than 1 over squared n, because otherwise, using theorem 3, you would find an entire interval whose probability is bigger than 1. So theorem 3 is the strongest statement here. And that's what I'll show you the proof of. And the second comment I want to make is that theorem 3 actually, it's not true if you replace 4 with 2, which is a real obstacle to a mental block for us when we were working on this, to try and hope that something like this will be true. If you replace 4 with 2, then the example of the parities that I showed you, So if you consider a rectangle where the product of the x's is 1 and the product of y's is 1, then in this rectangle, the probabilities for k and k plus 2 for the right value of k will be quite different. So there are rectangles where if the difference of the probability is large for k and k plus 2. But we're going to show that that cannot happen for k and k plus 4. Okay. And this is, I think, a really, for me, a surprising feature of our proof, because ahead of time, it would be very hard for me to imagine a proof technique that can distinguish the 4 from the 2. Sort of in my intuition, everything is like a Gaussian. You know, it's sort of continuous. And so if something doesn't work for nearby points, then it shouldn't work for the next point over. But I'm going to show you what we discovered, which explains why this happens.
But Anup, isn't there, you know, of course you gave the parity example, but in general for these problems, and there are other results in extremal combinatorics about, let's say, intersections of sets of, you know, where this parity, you know, even though in the Gaussian space all looks the same. I mean, if it was not plus minus 1 and it was bits, then it would be the difference between 1 and 2 as opposed between 2 and 4. And
yeah.
right, and you see why. One is the sort of, there is a natural parity, you know, special case where you see why it wouldn't work for 1. I guess here it's because you shift to plus minus 1, and then it's a difference between 2 and 4. But basically, I mean, I think in general, often there are what people call local obstructions that obviously should be avoided, and at least there's some intuition why it wouldn't work for 2.
Yeah, certainly there are many examples where similar things happen. It was just hard for us to imagine how the proof for this problem in this case would avoid it, because the proof would have to avoid k equals 2 here. And all the proof ideas we come up with, it's hard to see how they would tell the difference between the two. That's the, I think, so just to give you, so what actually happened is we thought there was no way that our proof would resolve the exact gap Hamming problem for this reason. So we didn't even try. We actually wrote a paper about the gap Hamming problem. And a year later, after we put the paper up on arXiv, we noticed that it solves the exact gap Hamming problem. So actually we were surprised. And it's not because it doesn't happen as a result. It's just that it didn't seem like ahead of time that the proof was going to do that. And I'll show you why the proof does it. Maybe you will see. Okay. So let me just say in pictures what we're saying here. So what our result implies is that if you take if you take a large rectangle and you look at the distribution of the points of the inner products inside that rectangle, then you know, one thing that one way the picture could look is it could just be the binomial distribution, right? So this could certainly happen. This makes sense. This is a possible distribution here, and that might look something like this, where it's monotone decreasing. It could also be like it could be different from the binomial distribution in the sense that the probabilities could go up and down. Okay, and in fact, I can construct examples of rectangles where this really does happen.
Look, we don't see your screen.
Oh, thank you. I think it happens if I stop changing slides for some period of time. Okay, so let me go back one. Yeah, so I'm just saying, you know, so here are some pictures just to make concrete what this theorem is saying. It's saying that if you take a large rectangle, you know, it's possible that the distribution you get of the inner products looks like the binomial distribution. This is the binomial distribution. It's possible that the distribution is not monotone. You know, the probabilities go up and down as you change the values of k. And in fact, I can construct examples where this happens. Okay, so there are rectangles that generate this kind of distribution. This is also possible. This is related to the counterexample we saw. It could be that, the probability of seeing 0, 4, 8 is, 10 times bigger than the probability of seeing 2, 6, 10. So this could also happen. But what our theorem asserts is that this cannot happen. It cannot be that you have just these 2 points with very different probabilities. All right, so there are 2 corollaries to this. The first one is something we already discussed. So it implies that actually the probability that you see any fixed point is at most 1 over squared n. Because you can take a window of, if you see a single point with a large probability, you can take a window of points, and this theorem implies that all of them will have large probability, and that cannot happen. A second corollary, which maybe actually I will skip, is that this theorem actually is strong enough to give a lower bound on the exact gap Hamming problem. The reason it works is you can actually use any protocol for the exact gap Hamming problem to sample a large rectangle where if x and y are uniformly distributed inside the rectangle, then the probability of seeing both squared n will be large, or minus squared n will be large. And as soon as one of them is large, the other one also must be large by this theorem. That's roughly what happens. And so you get that any protocol with small communication must have high error, because its typical rectangles see both squared n and minus squared n at the same time. But I think there are some confusing details. It's only half a page to write the proof, but there are some confusing details, so maybe I won't talk about them now. Okay, so in the rest of the talk, I'm just going to focus on explaining how we prove this theorem. All right, and the way we do it is we use ideas that come from a long tradition of studying anti-concentration bonds, going back to perhaps the question of Littlewood-Offord that was eventually resolved by Erdős. So this is now a slightly different setup where this was studied in mathematics. The setup is, imagine that y is uniformly random in the cube, and x is a real valued vector where none of its coordinates are 0. And then the question that Littlewood-Offord asks is, what can you say about the inner product? What can you say about the distribution of the inner product of x with y? And what was eventually shown by Erdős is a tight bound that for any number k, the probability that this inner product is equal to k is at most 1 over squared n. And Erdős's proof actually was very nice, very simple. He just observed that for any fixed k, the set of y that satisfy this identity, they form an anti-chain in the cube. That's his observation. It's a pretty nice and simple observation. And then once you know that that's true, the largest anti-chain is the middle layer of the cube. This is something we know how to prove. So that gives you the bound 1 over squared n. Okay. And since then, there was a little bit of an industry in understanding these kinds of questions. So you could, for example, prove stronger results. Here's one example. If the coordinates of x are actually distinct real numbers, then you get an even stronger bound. The bound is n to the minus 3/2. So this bound is realized when x is just the all ones vector, right? If x is just the all ones vector, then this is just a binomial distribution. And in fact, this is the correct value for the maximum probability. But if the coordinates of x are distinct, you can get a stronger bound. And in fact, there's a whole spectrum of results here. You can look at the additive structure of the coordinates of x And this additive structure, there's a parameter that you can measure that actually gives you exactly what a different bound for every x. It's really beautiful stuff. Okay. And what we're going to do actually is use an approach developed by Halaj to answer these kinds of questions. And what he did was figure out how to use Fourier analysis to address these questions. And in fact, the approach gives this kind of answer, but also all of these kinds of answers in a very nice way. So that's what I'll show you next. And then we're going to tailor, eventually we're tailoring the same approach to understand the inner products in rectangles. So what is Halash's approach? For simplicity, I'm going to change the setup now to avoid some technical details. Let's imagine that x is an integer valued vector. All the coordinates are non-zero, and y is uniformly random in the cube. Then here's the first step. The probability that the inner product of x and y is equal to k, you can express that like this. So imagine that theta is uniformly random between 0 and 1, a uniformly random real number between 0 and 1. Then what I have here is e to the 2 pi I theta and the difference of the inner product from k. Now the point is, when the inner product is equal to k, so if you fix y for which the inner product is equal to k, this is 0. And this expectation just contributes 1 in that case. Okay. But if the inner product is not equal to k, then it's some other integer. And then this difference is a non-zero integer. And then this expectation, when you take it over theta, you're going around the circle some integer number of times. So the average will just be 0. Okay, so this thing just captures exactly, it's measuring the fraction of the time that the inner product is equal to k. And once you have this, you can start working with this expression. So you can use the triangle inequality. You can take out the e to the 2 pi theta k component. Okay, and bound it like this. And now this e to the 2 pi I theta times the inner product is just a product of exponential terms. But the coordinates of y here are completely independent. So that's very nice. It means the expectation of the product is the same as the product of the expectations. And the expectations you can calculate just directly. It has a nice formula because this yj is a random bit, so either +1 or -1. So when you take the expected value of this, it's just the real part of this number. Okay, so that's just cosine of 2 pi theta j, xj. And now we just want to know what is the expected value of this product of cosines. So it's some integral of the product of cosines. And this I want to show you. It's pretty straightforward to bound it. You can bound it by 1 over squared n.
Aren't you missing a factor of 2 to the n for all the halves?
No, I don't think so, because these are all expectations. So y is also an expectation. Everything is an expectation here. So there's a 1 over 2 to the n in the.
I see. Thank you.
Okay, so here you get 1 over squared n. In fact, I talked about how if there's some nice additive structure of like the coordinates of x are distinct, you get stronger bounds, and it's this exact same approach. You just if the xj's are distinct, you can use the fact that these cosines are moving around at different phases, do a little more calculations, and you get n to the -3/2. Okay, so and in fact you can prove all kinds of results once you have this starting point. Okay, so this is what we learned that got us on this, started thinking about this path. And so in our setting, we're going to try and use the same approach, except there's one big complication, which is that y is not uniformly random, right? Y is going to be a random point in some large set. Nevertheless, we want to use the same kind of approach. Okay. All right. So now let me say how we do it. So here's a theorem we prove. It's sort of our main technical theorem. It says that if you have a large rectangle, then except with exponentially small probability of the choice of x, this quantity here, this is for every theta, can be bounded by something that's exponentially small in n times a term that looks like sine squared 4 pi theta. And I'm going to give you some intuition for, I won't show you the full proof of this theorem, but I'll give you some intuition for how the proof works. I think enough for you to understand. And what's really important here is this 4. This is exactly the 4 that the k versus k plus 4. It's the same 4. If I had here 6, that other theorem would be k versus k plus 6 have the same probability. It's this 4 is somehow very important. When we proved this theorem, we did not understand that this 4 is very important. Only later we observed that it seemed to just avoid the counter exam. Okay, so let's take this statement for a given just for a second and see how it implies the rest of the theorem. The theorem I've been stating, this one. So you once you have this, you just do, there's only one thing to do. So we have this identity which Halas wrote, right? And I'm just going to, I want to know the difference of these two numbers. I'm just going to substitute this identity twice, here and here, take the difference, see what happens. And when you do that, the only difference between, here you have k and here you have k plus 4. So that's just going to give you in one case minus k, and then in the other case minus k minus 4. Right? So what ends up happening, you apply the triangle inequality, you apply this theorem, there's some approximation here, okay? There's some exponentially small probability of errors that I'm dropping. But what ends up happening is what's written here is the part that's like e to the 2 pi theta times this inner part. That's what I can approximate by e to the minus n sine squared 4 pi theta. And the remaining part, comes out, and this 4 translates into something like e to the 4 pi theta minus e to the minus 4 pi theta. This corresponds to the difference in phases that comes from k versus k plus 4. We're subtracting the term for k minus the term for k plus 4. So that's what you end up getting. And here you have e to the minus n sine squared 4 pi theta. That's the common factor. And this thing is proportional to sine of 4 pi theta. Okay. So now here's the magic. So you have sine 4 pi theta here and sine squared 4 pi theta here. And that means you can now bound this integral. It's not hard, and you get 1 over n. The reason it's so small is that whenever this sine term is, whenever this term is small, it means the sine here is close to 0. But in that case, this sine is very close to 0, so it's small. So sort of these two terms in the product are never large at the same time. But if I were to replace, instead of 4 here, if I wrote 2, what would happen is I would get here sine 2 pi theta. I would have different phases here and here. Then actually there would be a region, some values of theta, where both terms would be large at the same time. And it would end up giving me a bound of like 1 over square root n here, turns out. So when these numbers match up exactly, you get 1 over n. And if they don't match up exactly, you get 1 over square root n. That's what ends up happening. So now let me say a few words about where this 4 comes from. sorry. Sorry about that. I still get scam calls from New Jersey. My phone is still there. Okay. You can also see my screen, I hope. So now let me say a few words about how we prove this theorem and where this 4 comes from. So in our setting, the coordinates of y are not independent, okay? But what we're going to do is we're going to expand this expression coordinate by coordinate and use a chain rule, for y, for the distribution of y. So we look at this quantity and we square it, and I want to write it like this. So you can think of it as just the expectation over the first coordinate of y. And then you get something that's the contribution of the first coordinate, e to 2 pi theta x1 y1, times an expectation that's the contribution of the remaining coordinates, all the future coordinates of y. And let's call the contribution of all the future coordinates a new random variable z sub y1. Okay? The expectation over all the future coordinates z sub y1. So this is the thing that we want to bound. Okay, and we're going to use induction. So I'm going to say bound this in terms of I'm bounding here the magnitude of a complex number. I'm going to bound it in terms of the magnitude of z sub y1.
So z sub y1 just hides the conditioning of the value of y1, right?
Yes. Once you fix y1, z sub y1 is the expected value over the remaining coordinates, conditioned on that value. So z, yeah, okay. Now, let me show you some intuition for where the 4 comes from or why you should be able to bound this. So let's imagine we're in the case where the coordinate of y1 actually has entropy. So it's a random bit. This is the entropy, in this case, there are potentially 2 values of z1, right? If y1 is 1, you have a value of z1, and then if y1 is -1, you have z minus 1. So what happens is this expectation, we're taking the average of those 2 values after a phase shift, right? What this thing is doing is just rotating the phase of these numbers. And if x1 is 1, the z1 term is rotated in this direction, and z minus 1 is rotated in the opposite direction. If x1 is -1, z1 is rotated clockwise, and z minus 1 is rotated counterclockwise. Intuitively, one of these 2 choices of x1 will lead to a big cancellation, right? Because it might be the case that z1 and z minus 1 were set up so that when you set x1 to be 1, both of these are rotated to the same phase. And then when I take the average of them, I get the magnitude is the same as before. But in this case, I would expect that the opposite choice of x1 would rotate z1 and z minus 1 to be very far apart on the circle. And then when I take the average of these 2 numbers, I'm going to get a big cancellation. The magnitude will go down significantly. This is the intuition. And that's exactly what we managed to show. So in fact, we show that depending on the value of theta, if y1 has entropy, half the choices of x1, you can, for half the choices you can bound, or for one of the choices of x1, you can bound this by e to the minus sine squared 4 pi theta times the magnitude of, expected magnitude of z y1 squared. And why this 4 pi theta shows up, if you look at this picture, you can see why it's necessary. There are some values of theta for which both choices of x1 are problematic. If theta is like a half, you're rotating halfway around the circle. Then if z1 and z minus 1 are in the same place, then it doesn't matter how you rotate. You'll end up at the same place. You'll end up at the same place on the opposite side of the circle. If theta is a quarter, also you have a similar situation where you could put z1 and z minus 1 on opposite sides of the circle, and then both choices of x1 lead to a situation where there's no cancellation. So these are pathological cases where you really don't get a win for those values of theta. And then you do some calculus to figure out what is the win that you get in general. and this is the win. Okay. So I won't show you how to calculate that, but it's not too hard. So that's the idea. So in the case that y1 has no entropy, we're just able to use convexity to bound this expression by, we can just continue expansion. So that's an idea of the whole proof. So eventually what we do is we use some encoding arguments to show that if x and y come from this large rectangle, there must be omega n coordinates of y where there is significant entropy when you expand them coordinate by coordinate. And most choice of x from this rectangle will make the right choice on those coordinates of y. If this was to the 0.99, and then you get nothing, because it could be that the coordinates of, well, maybe I won't discuss that. Okay, this is what we should. Yeah. So we find a linear number of coordinates of y that have entropy, and these arguments are really not very complicated to find those coordinates. They're somewhat standard coding arguments.
We could say if it was 0.99, then y could be just a single vector. There will be no entropy in y whatsoever.
Oh yeah, that's true. But I guess I was going to discuss the slightly more a different example where the coordinates of y that have entropy correspond to exactly the places where x makes the bad choice. So that's another way with the pictures. There's a broader kind of counterexample, right? It could be that whenever y has entropy, x is making a terrible choice. But you see, if you really have entropy in both x and y, then there are forced to be places where x and y are simultaneously random, and then x cannot avoid making a good choice in that picture. So you will actually get cancellation. Okay, so that's all I wanted to say in terms of technical details. Along the lines of these stronger results proved for just the anti-concentration of random vectors in the cube, we actually proved similar results as well. For example, we showed that if you take, instead of picking the cube, if A is a subset of coordinates where the coordinates are distinct, okay, so the ith coordinate is plus or minus I, for example, then you basically, for the same problem, you get even the corresponding stronger bounds. Instead of 1 over squared n, you get the probability of seeing any fixed value of k is closer to n to the minus 3/2. An open question here is that for some strange reason, we end up with a factor of square root log n in this case. And I don't believe that this square root log n should be here. Just like we actually proved the results here in the almost a full generality. So there's a full spectrum of results about anti-concentration results. We generalize them to rectangles. Okay. And they correspond to giving communication problems that have stronger and stronger, that have communication lower bounds even under weaker assumptions on the promise. That's what it corresponds to. Okay, so that's all I wanted to say. Thank you.
Thank you, Anup. A clap for everybody. So questions to Anup?
I have a question. What's the intuition behind the n to the minus 3/2 when they're all distinct?
It's actually tight if you take the integers 1, 2, 3, 4 up to n, and then you can see that they're sort of if you have a few minutes, actually, maybe I can almost state the most general form of the bound. That's even more. So it's tight. You can check that it's tight for the integers 1, 2, 3 to n. So that's why it happens. I'm not sure that I have any more intuition about that.
No, I think that's good.
Maybe I'll say that in general, what happens here is for every L, Wait, can you see my screen?
I'm not sure it's the screen you want us to see. We see it.
Oh,
Oh
okay.
yeah, yeah, it's good.
Okay, I was right. Yeah. So here's happening. Here's one way to capture the result for n to the minus 3/2. Look at solutions to the equation.
Actually, never mind. I think we're not. Oh yeah, we are. Sorry.
Yeah.
There's a delay, but it's good.
Okay, look at the solutions to the equation. Epsilon 1 is equal to epsilon 2, where epsilon 1, epsilon 2 come from the set x1, x2, xn. Now, how many solutions are there to this equation? If the coordinates are distinct, there are exactly n solutions. You know, epsilon 1 could be, both of them could be x1, both of them could be x2, both of them could be x3. And that's much smaller than picking a random assignment of epsilon 1, epsilon 2 from this set. Okay, the number of ways you can pick them randomly is n squared, and only n of them give you a solution to this equation. That explains n to the minus 3/2. In general, if you have an equation of the type epsilon 1 plus epsilon L equals, let me write mu1 plus mu L, where all of these variables come from the set of numbers x1, x2, x3 to xl, the number of solutions to this equation say something about anti-concentration. So you can count the number of solutions to this equation, and if this number of solutions is substantially smaller than the total number of ways of assigning the numbers x1 through xn to these variables, you get very strong anti-concentration bounds. So this is the most general form of anti-concentration that you get from the approach of Halash when you work everything out.
To those people who still remember Tom Sanders' talk about the arithmetic progression, this is related to a different way to think about the notion which he called the additive energy of a set. And this type of notion is, well, it's really capturing what Anup says, the arithmetic structure within a set of integers. So the solutions to this type of equations.
Right.
And two random samples have the same value. That's sort of the additive energy. And when he talked about other notions.
Tony, maybe I can. Hi, Anup.
Hi.
Maybe there is some. This is not a proof of anything, but a square root n bound for the binomial distribution, you can see from the variance or from the standard deviation of summing the thing. The variance of summing the number 1, 2 up to n is n to the power 3, which means that the standard deviation is n to the 3/2, which is this thing.
Yeah.
More questions? Okay, I have a comment to many in the audience who are at the Institute. This collaboration, long and fruitful collaboration between Amir and Anup started when they were postdocs here at the Institute. So we've seen a lot of this happen over the years and hope it will continue to happen. Any other questions, comments? All right, thanks, Anup. Thank you very much.
Thank you.